Today we will be doing for week assignment one or two
For
questions
two, for two.
or two.
Yeah,
Okay, sir.
yes.
Nice.
So I'll be
Okay.
discussing some problems related to your
Okay,
study material from week 2, and these
okay,
problems
sir.
will be similar to the assignment 2. Okay.
Okay, sir.
So before we start, if you have anything in particular that you want to ask,
But we can
feel free to ask.
week two classes I didn't see, sir, not yet.
Okay.
So
No
that's
problem.
why.
No problem. So what I'll do, I'll just give a very brief intro, like summary of
Okay,
what is discussed in week 2 sessions.
okay,
Okay.
sir.
So so that you are able to then follow along the problems that we'll be solving.
Yes, sir.
And if you want me to elaborate upon any topic while I'm giving the
Yes, sir.
summary, yeah, please stop me and then I'll happily discuss it in detail. Okay.
Okay, sir.
Okay. Okay, so I'll share my screen. Yeah. Okay. Okay, seems like we are the only two people here.
Shall we'll wait for sir, two or more minutes, sir.
Okay, we can wait. No problem.
Otherwise, I can also join in 7 o'clock also.
No, no. See, anyway, I'll be here for 2 hours. If even if
Okay, sir.
nobody joins, I'll still have
Yes.
to be here for the session and solve all these problems.
Okay, sir. Whatever.
Yeah, yeah,
Let
yeah.
me
So if
also.
this time is comfortable for you, then please hang on. And if you
Okay,
want
sir.
to
This is
join later, then
comfortable
it's
for
up
me.
to you. Yeah.
No, sir. This is comfortable for me.
Okay, okay, okay. May I ask
Sir,
what degree are you
yeah,
pursuing?
sir. Actually, I am a teacher, sir.
Ah, where?
I want to press up all the old things what has gone back.
Ah, okay.
So just for my
Yeah,
interest only. I don't have any use of these things. This
okay.
credit's not going to give, just for knowledge gain.
Good, good. So you are a learner. I see.
Because I have done my through correspondence course, sir.
Ah, okay.
That's why I want to see some more.
Okay, okay. No, that's great actually that you are still here. Uh, it shows you are enthusiastic about learning, which is good. So,
Thank you, sir. So we can start from simple problems. You can start.
okay, sure. So, I'll just briefly recap, okay, what
Yeah.
what all topics we will cover, and if you want explanation of any topics, just let me know. Okay.
Yes, sir.
So there will be a few problems which will be based on infinite square well or
Okay.
particle in a box.
Yes, sir.
Okay. We already discussed a few problems in the last week's session, which were
Yes,
based on
yes, sir.
particle in a box. Yeah.
I was there. Yeah.
Great. So few more. So then you know what is the energy and what is the wave function looks like.
Yeah, sir.
Then also what we will have is we will have harmonic oscillator.
Yes.
Okay, where we know that the energy is quantized, right? It is
Yes.
n plus half h cut omega. And then we'll have this time some potential barriers
Okay, sir.
of some finite height, and then um, basically tunneling, right?
Yes.
When the energy of the particle is less than the height of the potential barrier, still there is some
Okay.
probability that it tunnels through. So there will be a few problems on that. And then related to tunneling is something known as transmission coefficient
Coefficients.
T, right?
Yes.
Okay. Yeah, so this is more or less the things that we will solve today. Okay, so I have already
Oh,
collected few problems.
yes, sir.
Now this is the first one. So let's go through this. So we have a particle. We are given that it has mass m, okay, and
Mm.
it is confined to move in a potential. So we are given a potential like this.
Yes.
Just by looking at the potential, we can say that this is a 1D problem, right? Because
Mm.
we only have x, and this is a particle in a box type problem.
Okay, sir.
Okay, so if we draw our x-axis,
Mm.
this is, let's say this is our x-axis. Let me just straighten it up a bit, and this is 0, and this is a.
Yes, sir.
So inside the potential is 0, and outside the potential is
Potential
infinite.
is, yeah.
So the particle is confined within this region.
Okay, sir.
Okay. Now we
What
are
is asked,
given,
sir? Mm.
yeah,
Mm. Without normalized function. Okay, sir.
yes. So we are given a wave function.
Mm.
We are given a wave function at time t is equals to 0. So let's just write psi x, and this is a
Yeah.
times sine 5 pi x by a and cos 2 pi x by a. And then we have to find out the normalized wave function, right? So the question
Yes.
asks what is the normalized wave function. And if we look at the options, we see that
Mm.
the wave function is written in terms of sums and not product. So in the question here, it is a product
Yeah.
of two trigonometric
And
functions, and here it is a sum of trigonometric functions.
okay, sir.
So intuitively, the first step that I think we should consider is that we should convert this product to a sum,
Yes, sir.
right? So we have the trigonometric identity sine alpha cos beta. We can write this as half
Mm.
of sine alpha plus
Of
beta
course.
and sine of alpha minus beta, correct?
Yes, sir.
Okay, so then let's substitute for alpha and beta, and our wave function becomes psi of x. This will become a by 2
A by 2.
and sine. So adding this will give us 7 pi
Mm.
x over a, and then subtracting
Minus
will give us
5. 5 by. Mm.
5 minus 2 is 3. So it's 3, right? Sine 3 pi x by a. Okay, so
Yes, sir.
it's either
Mm.
option B or option D just by doing this step.
Yeah.
And now
Mm.
to find out whether it's B or D, we have to normalize this wave function. Okay, so this is our wave function, and then what we can do is, if we just look at this form now, if we look at this
Okay.
form, it is in the form of sine n pi x by a, correct?
Yes, sir.
And when we
Normalization. Mm.
and when we consider the wave functions of a particle in a box,
Mm.
so they are generally written like
Root
this,
2 by A. Okay. Mm.
correct?
Yes, sir. Yes, sir.
So what we will do is, we will, so here n is, for example, here n, if we compare these terms, so here n is 7 and
7 by
here
8.
n is 3. Okay, but
Yeah.
here they are not normalized. So what we will do, so we'll write them out separately. Sine
Mm.
7 pi x by a, okay, plus again a by 2
By
sine
2.
3 pi x by a. And just by comparing, we know that this term should have been
Yeah.
root 2 by a, correct? And here
Yes,
also
sir. Yes, sir.
this term should have been under root 2 by a.
Okay.
So we get a by 2 is equals to under
It's
root 2 by
wonderful.
a. So our
Mm.
a becomes
Root 2 by. Mm.
2 root 2 by a. Sorry, this will be like this,
So, yes.
correct? So 2 under root 2 by a. So we have found out a,
Yeah.
and then basically what we have to do is we have to do
Normalize.
this. So we have to, yeah, then substitute this here so that our psi of x is normalized. So we see that we are getting a factor of 2, right?
Yes.
So correct option will be B, which has this factor of 2.
Okay, sir. Definitely.
Okay.
Good, sir.
Okay. So yeah, clear.
Sir, in actually in examination now, uh, the questions will be of this type of questions, or the questions will be more than this level. Now we are solving in examination.
I cannot say for sure, but since
Yeah.
like these problems that I am solving, these are from previous year's problems.
Okay, sir. Okay.
So you can basically take them as a reference that this will be the level of the problems.
Yes.
Okay.
Okay, sir. Thank you, sir.
Okay.
Mm.
So let's look at the next one. Okay. So we have a harmonic oscillator here.
Yeah.
It is given that
Everyone is-
we have harmonic oscillator and it is in ground state. And we are
Yes, sir.
given that this is the wave function of harmonic oscillator in the ground state. Okay. And then
Yes.
what we are asked is the probability density is
Yeah,
maximum
okay.
at x is equals to 0. We have to say whether this statement is true or whether the statement is false. So let's write down our ground state wave function,
Yeah.
m omega upon h cut pi. So this is simply a constant, right?
Mm.
Everything here is a constant, and the x dependence comes here. And because they are asking whether it is maximum at x equal to 0, so first of all they are asking about the probability density. So we know that the probability density
Mm.
p of x is
Is
given
equal
as
to mod of
psi
size.
of
Yeah.
x squared.
Size square.
Yes. So let's square this thing. So then this power simply becomes half. instead of 1 by 4,
1/12. Mm.
and exponential minus m omega x squared h cut. Okay, so this was,
Oh,
instead of 2 h cut, we now just have h cut here
okay.
because we have squared this thing.
Yeah.
Correct?
Mm.
Okay. So now, when we want to find out where the maxima of any function is, so we have to differentiate it. Let's
Acha.
differentiate p with respect to x. So this is a constant, right?
Yeah.
So it remains same.
Same.
And here we will have minus
M omega.
m omega 2 will also come, right?
Yeah.
Okay.
-2 m omega.
Minus 2m omega x by h cut, and then same thing. So exponential m omega upon h cut by
That
half,
is minus.
sorry, minus m omega x squared by h cut. Yeah, this thing.
Yes.
And then let's set it to 0 because we want
Yes,
to
sir.
find out the maximum.
Yes, sir.
So its first derivative is 0,
Mm.
and clearly this gives us, so this is a constant, and this is, all this is a constant, right? So this,
And this all things.
all this
Yeah.
is just constant. So
Mm.
we have x into exponential minus m omega x squared by h cut. Okay, 1 second. Yeah. Okay, this is 0.
Yeah.
So
Yes.
this means that either x is very large, like x is infinite, then the second term
Mm.
will become 0,
It's very small.
or simply x, when x is 0, then also this equation is satisfied. And
Yes, sir.
they are asking whether it is maximum at x is equals to 0. So what we know that I now at x is equals to 0, this derivative is 0. So either it is a maximum or it is a minimum.
Minimum.
Okay. Now to find out whether it is a maximum or a minimum, we take second derivative. So d2v by dx squared. So again, this was entirely, all this was a constant. Let me just call it
Mm.
a.
Yeah.
And then here we have these two terms, right? So this will give us exponential minus m omega x squared by h cut. Okay, somebody wants to join. So now we have one more person.
Yeah.
Okay. Hi. So we are in the middle of solving one problem. Maybe you can you can follow from the next one if that's okay with you. Okay.
Yes, sir.
So here, um, yeah, and then we will have a times x,
Let him X.
and then minus, and then basically something. But since we are calculating this at x is equals to 0, so this term will
Yes,
be
sir.
0.
No, automatically. Okay. Mm.
Yeah, correct. And then
Yeah, sir.
if we look at this coefficient a, and this is, if we put x is equals to 0, so we are only left with a, right?
Mm.
We are only left with a. And if we look at our a here, which I have circled in yellow, it is
Yeah.
less than 0, correct? Because we have this negative
Mm.
sign here,
Yeah, yeah.
correct?
Yes, sir. Yes, sir.
So
Yes.
our second derivative is negative and our
So,
first derivative is 0, which means that the probability density in
well,
D is maximum at 0. So the
true,
correct
sir.
answer is A.
True.
Okay. Yeah.
Yes, sir.
Any doubts in this one? I hope it is clear.
No, sir. Nothing. I can follow.
Okay.
Okay, sir.
Okay. Yes. So, hmm. Next one.
Mm.
And here again, this is particle in a box, right?
Particles. No, yes, sir.
It's similar to the first problem, but in first problem we had 0 to a, here we have minus a to plus a.
Having minus a to plus c.
Yeah, so symmetric kind of potential about 0. Okay. And what they are asking is that the probability of finding the particle between x is equals to 0 and x is equals to a over n when it is in the nth state is 1 by n. We have to tell whether this is true or false.
Where when it is in the nth state. Okay, sir.
Yeah,
Okay. Okay.
yeah, yeah.
Mm.
And notice that they are asking about a particular region.
Re- X is equal to 0 to x is equal to a by n.
Correct.
Mm.
So let me just draw the x-axis. Let's say this is our minus a, this is our plus a, and let's say this is 0. So what they want to know is that in this region between your 0 and when
Mm.
n is 1, so when n is 1, so our uh, region of
Maximum.
interest will be this
Mm.
one. This is for n is equals to 1.
Okay, sir.
When n is 2, it will be a by 2, right? So
Yeah.
just this one, n is equals to 2.
And it's,
And
yeah.
similarly, n is 3, so a by 3
Then
somewhere here. So this region constantly keeps on decreasing.
decrease.
Okay, and they are saying
Yes, sir.
that this probability when it is in the nth state, so the probability of finding the particle in this region, it is 1 over n.
Yes, sir.
So true or false? So what we can do is, okay, there are two ways. If I had to just take a guess, I'll just look at some simple cases like when n is equals to 1. I know this is a symmetric
Oh,
potential,
yeah.
and when n is 1,
Mm.
so here, so the probability of finding the particle from x equal to 0 and x is equals to a. So 0 and a, what will the probability of
Mm.
finding the particle in this region? I think it should be 1 half, right?
What? Yes, sir.
It should be half. It should not be
Half,
1.
half.
But this
One.
formula is already giving me 1, right? So if I had to just guess, maybe it should be false. Correct?
Yeah, definitely.
Correct? But maybe they are asking about the higher states, right? Maybe they
Yeah.
are talking about the excited states, and we don't have to consider this n is equals to 1 case. Okay.
Okay, sir.
Or maybe sometimes there is a typo in the question that instead of minus a to a, it is 0 to a. You never know. So instead of just doing this guesswork, why
Uh,
don't we actually find out what the probability is?
yes, sir. Sure.
Okay. Okay. So let's write down the wave function. So we know wave function we have written in the first problem also,
Root 2 by A.
sine
Fine.
n pi x over a. That is correct, right?
Yes, sir.
And then we also have written the probability density p of x, which is just the square of this thing. That will be,
Sine square and phi. Okay, sir.
and then when we have to find out the probability p, we integrate this probability density from 0 to
0 to L.
x, and here our x is a by
A,
n.
N, A by N. Yes, sir.
Correct? This is our upper limit.
Yeah. Yes.
Okay. And then just put probability density multiply by dx. Then we substitute for our p of x, and what we get here, we get a
1 by
sine squared function. Okay, so this is what
yeah.
we have now. Now what we will do, we will write
To
this
integrate
sine function.
by A.
Okay,
1 minus cos square.
somebody wants to join. Yeah,
Check.
hello. Yeah, okay, welcome. We are currently in the middle of a problem. uh, do you want me to go over the problem again, or should I just continue?
Yeah, please, if you can. Thank you.
Okay, I
Have
can.
you just started? Is it the first question?
That's
No,
it. The
this
third
is the,
question. Third.
yeah, this is the
Okay,
third
okay,
question.
okay.
Anyway, I'll just give you a very brief intro to this problem. So we have a particle of mass m, and it is inside a potential given by this. So this is a particle in a box, right? So between minus a to a, the potential is 0, and outside it is infinite. So particle in a box. And what the question is saying, that the probability of finding the particle between x is equals to 0 and x is equals to a by n, where n is the state of the particle. So this probability is actually 1 by n. We have to tell whether this statement is true or false. So for example, let's say our n is 2. So the probability that we have to find is between x is equal to 0 and x is equals to a by 2, and check whether the probability is coming as half. Okay, so what we have done, we have written our wave function psi of x under root 2 by a sine n pi x by a. This is for the nth state, correct? So in nth
Yes, sir.
state, the wave function looks like this. And then if we square the wave function, so we write our probability density p of x, which is nothing but mod psi squared, right? And our wave function is real, so we can simply square it. Okay, and then because we have to find out probability between 0 to a by n, so we have taken these as our limits. So from 0 to a by n, integrate px dx, and we have substituted for px, and it is a square of a sine function. So this is where we were. Is this clear, or you have any doubts?
Okay.
Yeah, okay, good. So now we wish to solve this integral. So what we will do is we will write this sine squared. Okay, let me put the limit. We will write this sine squared as 1 minus cos.
Cos 2.
Sorry, this was 2, right?
Mm.
This was 2 by a. Okay, so this will be 1 minus cos 2n by x by a, and then we have to divide the entire thing by 2. So let me just take that 2 outside.
Okay.
Is this okay?
First thing. Second part will be 0.
Yeah, correct. So second part will be 0. So it is just 1 over a, and then this is integral dx 0 to a over n, and then minus integral cos of 2n pi x by a 0 to a by n dx. Now this will become a sine function. So integration of
Yeah.
this will give us sine, and sine at 0 is 0, and when we put x as a by n we get 2 pi. So sine of 2 pi is also 0, right? So sine of 2 pi minus sine of 0. So therefore this entire thing, this one becomes 0. Okay, and what we are left with, we are left with 1 over a multiplied by a over n. So these two cancel out, and we are left
Yeah.
with 1 over n, which is what is given in the question, right? So
Yeah.
okay,
Okay, sir.
yeah. So next one, here we have an electron. An electron is confined in the ground state of a one-dimensional harmonic oscillator, right? So
Yeah.
how we draw the harmonic oscillator? We have this some kind of a parabolic potential, right? And then we have, this is our ground state, and then we have equally spaced states. Okay, so our electron is confined in the ground state. So here is our electron. What we are given is, we are given delta x 10 to the minus 10 meter. Okay, so 1 angstroms. If the expectation values of kinetic energy and potential energy are same, another thing that we are given is that T is V, then the energy required to excite the electron to its first excited state is, and they are asking what is the energy required to excite the electron to its first excited states. So basically this energy delta E.
Yes.
So we have electron in the ground state, we want to send it to the first excited state, and we want to know how much energy is required. The two things that are given to us are, first thing is that delta x is 1 angstroms, and second thing is expectation values of kinetic energy and potential energy, they are equal. Okay, so how can we make use of this? So first of all, using this thing, because our total energy is sum of kinetic energy and potential energy, so what we can then write is our expectation value here is simply half of total energy, right? Where E0 is the
1 by 2 H,
ground
H
state
cross.
energy, right? Because both these expectations values are same, so we can say that half of the total energy is potential energy and half of the total energy is kinetic energy.
Yes.
Okay, now since we have assumed this to be true, we know that potential energy can be written as half m omega square delta x squared. This is how we write the potential energy. and we know that our ground state
Okay.
energy
H
is
cross omega.
half h cross omega. Correct? Half h cross omega. Yeah.
Yes.
So essentially, from here, what we can do is we can find out our omega. So let's cancel out these halves, and our omega also gets cancelled, and this just becomes h cut by 2. Yeah. So this omega cancels out here, and what we can do is we can write omega as, okay, h cut over 2m and then delta x squared. Okay. Now we know
Okay, sir.
delta x, we know mass of the electron, and we also know the value of h cut. So essentially, we now we have value of omega. What will be this delta E? Because it is to the first excited state, our delta E will be E1 minus E0, and this will be 3 by 2 h cut omega minus half h cut omega. So simply just h cut omega. Now we can substitute for omega, and what we find is our delta E becomes h cut squared over 2m delta x squared. Yeah.
Yes, sir.
Let's substitute the values. So this is 1.05 10 to the minus 34 squared, and the mass is 9.1 10 to the minus 31, and delta x is 1 angstrom, so this is simply 10 to the minus 20. Okay.
Okay, sir.
Now, okay, let me use my calculator.
Yeah.
1.05 squared and divide by 2, divide by 9.1. So this becomes 0.0605, okay, into 10 to the minus, so this will be minus 70. So this is delta E. Okay. Let me write this as 6.05 into 10 to the minus 19 joules. But the question asks us to find out the values in EV. Okay. So let me quickly convert this to EV. So to convert this to EV, we have to divide this thing by 1.6 into 10 to the minus 19. So this just cancels out. So our delta E is simply 3.78 EV. Okay. Now this is a reasonable number that we are getting, right?
Uh, one one small problem. When considering the expression for the expectation value of potential energy, we have taken delta x square. So half m omega square into delta x square.
Yeah.
And why not just x square?
Huh. So okay. Let me write down here. So here what happens? Okay, I'll tell you here. So what we have, we can write delta x as under root expectation value. Sorry, like this x minus x. Yeah. Okay.
Yes.
Oh, I'm missing one square here.
Is it x square minus the expectation?
Yeah, it is x squared like this,
Yes, yes,
right?
yes, yes. Yeah.
This is the one, right?
Okay.
Yeah, yeah, you are right. So for for simple harmonic oscillator, for simple harmonic oscillator, what we know is that our expectation value of x, that is 0, right? Because it is a symmetric potential. So
Okay.
if we take the average
Mm.
around x, so the weight of the wave function, sorry, is distributed equally on both sides of x. So the probability on both sides of x is same. So the expectation value of x comes out to be 0. Yeah. And we can calculate in detail, but this is a simple way to find out that the expectation value of x will be 0. So when we put this here, what we will get? We will get, so let me write this as square here, okay? And let me remove this under root. So then what we get? This delta x squared is simply x square, okay? This is valid only for this simple harmonic oscillator, simple harmonic oscillator case.
Okay.
Yeah. So instead of writing half m omega square x square, we can directly
Yeah.
write delta x square
Okay.
because
Okay.
the
Thank
expectation
you.
value of x is 0.
Thank you.
Okay. Okay. Another problem here. And okay, so this problem has a typo. So let me just crop the options. We'll not look at the options for this one. Okay. We'll just solve the problem. So what we have here, again we have a harmonic oscillator potential, okay? And then we are talking about time t is equals to 0. The wave function looks like this. So this is at t is equals to 0. What we are to find is that the expectation value of energy as a function of time. Okay, so expectation of value of energy will be E, and we have to find it as a function of time. Now note that this is the ground state wave function because we have this psi 0 and here we have psi 2. So this is the second excited state. Yeah. And what we have written our total wave function psi as a sum of these two wave functions, and they have different probabilities. So the probability of ground state is 1 by 3 and probability of second excited state is 2 by 3. Okay, so let's solve this one. So our psi is 1 by root 3 psi naught. Okay, now we know that our expectation value E, this is simply P naught E naught plus P2 E2. Okay, now here our P naught will be 1 by root 3 mod square, which is simply 1 by 3. Our E naught will be the ground state energy, which is simply half h cut omega. Here P2 will be 2 by 3 mod square, which is simply 2 by 3, and the excited state, the second excited state energy will be, so it is n plus half, which means 2 plus half, which means 5 over 2. Yeah, so we can substitute all these four equations back here to find out the expectation value. So our expectation value becomes 1 by 3 half h cut omega, and then 2 by 3 5 h cut omega by 2. Okay, so clearly LCM is 6 and this is 10 and this is 1, so this is 11 by 6 h cut omega. Okay, got it.
Yes.
So if we look at the problems, you can see if I uncrop this, that no option matches, right? So I think they have written it as 2h cut omega, assuming that will get 12 by 6. So in such cases, if we have to select the closest option, it will be B. This is the closest to 11 by 6. Okay.
But where is the function of time here?
Yeah, so the expectation value of energy here is independent of time.
Okay, and this expression P naught E naught
Yeah.
plus P2 E2,
Yes.
how do we get that?
Sorry, just once again. Let me crop it back. Yeah. Okay, so this P is simply the probability, right? P is the probability that your wave function is, maybe somewhere in some texts you may have seen that you can write psi as, let's say, C1 phi 1 plus C2 phi 2 and so on. Like this is one of the conventions, right? That this
This,
convention is called superposition, right?
mhm.
Superposition. And then whenever we want to find out the expectation value of any quantity, let's say some quantity, anything, let's say q, some q, then basically what we do is we find out the basically what is the corresponding value of q for this phi 1, for phi 2, and so on, and then multiply it with their probability, corresponding probabilities. So mod c1 square, and then here you will have q1 and mod c2 square, and then here you will have q2, so on. So instead of writing this c1 mod c1 square, I have written p0 p2. Okay, so you can think of
Okay.
it like our wave function
Okay.
is combination of ground state and excited state, and the weight of the excited state wave function is more, right? So it's here we have 2 by 3 and here we have 1 by 3. So the probability of finding our particle is somewhat more in the excited state than the ground state. So therefore our this energy, right, the expectation value of energy, it will be more towards the excited state energy and less towards the ground state energy. How much more? That is given by P2 and P0. So our P2 is 2/3 and P0 is 1/3. Okay.
Yes.
Okay. 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 Now here again, this problem has a little typo, but yeah, we'll talk about that later. So yeah, let's solve this. They are saying that we have the probability density for particle to lie between, we have given a wave function psi of x, we don't know what this wave function is, this is the form of the wave function, okay, and between x and x plus dx we have to calculate the probability density. So we already discussed that probability density P is nothing but mod psi squared, right? So how do you write it? We write it like psi star psi. Okay, so if we take okay, so our psi is a to the power iota px by h cut plus b a to the minus iota px by h cut. So our psi star will be a star a to the minus iota px by h cut plus b star a to the iota px by h cut, right? And then when we multiply these two, we will get p. So upon multiplying, note that multiplying these two will give us a times a star, which is nothing but mod a squared, and these exponential parts cancel out each other. Similarly, multiplying these two will give us b times b star, which is mod b squared, and again these exponential parts cancel out each other, and then cross multiplying we get a times b star. Now these two will actually add, so this will become e to the iota 2 px by h cut and a star times b e to the minus iota 2 px by h cut. Okay, so this is the solution, right? But it doesn't match any options. Okay, and why it doesn't match? Because they have given this wrong constraint that we have to consider them complex. If we consider them complex, then this is it, we cannot simplify it further. To simplify them further, we have to assume that they are real functions. Okay, so let me write clearly that if a and b are real, then basically this a b star and a star b, we can take them as common, right? So then we can write our p as mod a square plus mod b square, and then let's write mod a mod b e to the 2 iota, okay, e to the iota 2px by h cut plus e to the minus iota 2px by h cut. Now we know that there is this identity. Yeah, so we can write p as mod a square mod b square plus 2ab and then cos of 2px by h cut. Okay, so does this match anywhere?
Yeah.
Yeah, it's option A. But this is only possible when we assume that A and B are real.
Yeah.
Otherwise, we cannot make this approximation. Yeah. Okay. Any doubts in this one?
Yes.
Yeah, okay. This is okay.
Yes. Okay.
Yes.
Okay. So let's take 30 seconds break. I'm having cold, so let me drink some hot water.
In the end, if you can just show me the first two questions that I missed, so that will be very
Sure.
grateful. Yeah, thank you.
No problem.
Yeah, thank you.
Okay. So I guess we are done with 6 questions, right? So yeah, let's go to the 7th. So they are saying that you have a potential barrier of height u naught. So let's draw a potential barrier. It should look something like this. Okay, and this is u naught, and the width is b. So this is b. Doesn't matter, right? So the position space wave function psi of x will be oscillatory. So they are asking psi of x is oscillatory if and only if energy E of the particle is greater than u naught, 0, less than u naught, negative.
C? Is it C?
Yeah.
Less than u naught. Okay, I'm not sure. I think it is A. Okay, okay. Let's do
Yes.
simple exercise.
Yeah, okay. Right, right, right. Otherwise, if it is less than u naught, then on the other side it will be decaying.
Correct, correct. Yeah,
Yeah, it will be decaying. Yeah? So if it is only if it is greater than u naught, it will not see that potential barrier actually.
exactly, exactly.
Yeah, that is
So
greater than u naught. Yeah.
when let me just
E-
write it out. When this is E is greater than u naught, so the solution generally goes like some iota kx, right? Like for a free particle. For a free particle, our u naught is 0,
Yes, yes, yes.
and then there is
It is like a free particle. Yeah,
right iota kx. So that is
yeah,
one
yeah,
proper way I can think
yeah.
of.
Right, 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 right.
And because of this iota term, we can say that this is oscillatory, right?
Oscillating.
Yeah, yeah.
Because of this
Yeah.
iota.
Yes, yes, yes.
And
Absolutely.
when this energy is less than u naught, then this iota somehow escapes and we have this decaying kind of a function.
Hmm, 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 hmm. Hmm.
So either it is growth or decay, but generally it is decay.
Yeah. Hmm. Right.
Something like that roughly.
Hmm.
Okay.
Yeah.
Okay. So yeah. So we are given an electron, a 1 eV electron that got trapped inside the surface of a metal. If the potential barrier is 4 electron volts and the width of the barrier is 2 angstroms, then the transition coefficient T is. So what we are given? We are given, let's draw a barrier again. Okay, sorry. Okay, and this is 4 eV and the width is 2 angstroms. And the electron is trapped inside this barrier. The energy of electron is 1 eV. Okay, let me write. So we have an electron and the energy is 1 eV. So it has less energy, but still there will be some probability that it comes out, right? And that is determined in terms of transmission coefficient T. So let's find out the transmission coefficient. Of course it won't be 1, so option A is wrong. Let's check for the other options. So T is given by this equation, that was okay. So this, the derivation of this was, I guess, discussed in the lectures modules of this week, so I'm not going to derive this, but this is a well known equation for transmission coefficient, right? And then we have minus 2, and then here we have this kappa L, where this kappa is given by okay. So if we put the values of V naught and E, so this is 4, this is 1, so this is 3, 6, so this becomes under root 6m by h cut, and then we can put the value of m and h cut here and find out what this kappa comes. So let me quickly open my calculator. This is 9.1 into 6. Okay, so this is coming out to be roughly 8.89 into 10 to the power 9 per meter. Okay. So then this term 2 kappa L, here our L is 2 angstroms, so 2 into 10 to the power minus 10, so just multiply this, so this term becomes roughly this thing. Yeah, so this becomes 3.56. Okay, so our T then becomes 16, and here E is just 1, V naught minus E is 3, and this is 4, so square, so this is 16, and e to the minus 3.56. Okay, so this cancels out, this becomes 3 into, calculate, 0.028, okay, which is 0.084. Okay, so this is T, which is close to this one here, so option D. So I didn't calculate very precisely, I think. So just missed 1 decimal place. Yeah, but we are very close to the answer. So okay,
Yes.
is this clear?
Yes, sir.
Okay.
Yes.
So we just have to know this formula in this one, and then we have to just plug in the values. Okay. Yeah. Again, uh, we have a potential step of this form. So it is V naught for positive x and 0. Okay, so it is a step function like this and like this, correct? So this is x0 here, so the potential is 0, and here it is V naught all the way. Okay, and now we have a beam of particles with energy E which approaches this potential step from left. So here we have a beam of particles, the energy is E, okay, and it is coming from the left side. Now the question is the statement that best describes the reflection coefficient R is. So the question is about the reflection coefficient R. Okay. So we have different cases. That one case is E greater than V naught. Okay. E greater than V naught, and the other case is E less than V naught. So if R is 0, R is 1, what is R? Okay. Do you want to guess which option is correct here?
When E is greater than V naught, then R should be 0.
Okay. If E is greater than V
V
naught,
naught, then R should be 0.
R should be
There
0.
should not be any,
Okay.
I think.
Okay. Okay.
So,
Okay.
but when E is less than V naught,
Yes.
then R is not 1. R will be, there will be some transmittance. Some exponential decay will, I think,
Hmm.
not sure. I mean, just get.
Okay. No, I understand what you are trying to say.
When E is greater than zero,
Yeah.
E is very very greater than V zero,
Yeah.
then there must be some reflection. There must be some reflection.
Yes. Yeah. 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 So okay,
Then
because okay, one thing that we should note is that this potential barrier is extending all the way to infinity,
yeah,
right? So let's consider the case when we have less energy. Okay, let's first consider that case when our E is less than V naught.
okay,
So here it cannot tunnel through this barrier, right? Because this is extending all the way up to infinity, correct? Are you getting my point? Because let's say
Yes,
if we had
yes,
a finite barrier, then we say okay, although our energy is less, then we not still it can tunnel through it. And the
yes,
thinner the barrier we make, we increase the tunneling probability. Now this is the extreme case where we have made it infinite. We have made the barrier infinite, so it can never tunnel through this.
yes, sir.
So when E is less than V naught, our particle will always come back. So it will always reflect. So our R will be 1. It may go in some for some distance and then decay. So its wave function will decay to 0. Right? Its wave function will decay to 0 all the way to 0 because it cannot tunnel. And then this decaying wave function means that it the potential has reflected it back. So when E is less than V naught, here R is 1. Now let's consider when E is greater than V naught. Now here our energy is higher, so we are somewhere here, right? Now because this is quantum mechanics, so there will be some finite probability that it is reflected back, right? Although it has higher energy, and then some probability that it transmits. Yeah.
okay, okay.
So
So
here
A, huh?
R is non-zero,
Non-zero. Okay,
and here R is 1. So this is A.
okay.
We are not sure what will be the R in this case, but we are
Hmm.
100% sure that in this case R is 1.
Okay,
Yeah. Okay.
yeah. See.
Okay. Okay. So I'll also just write down what R is. So here this, and here this is just R. So this is following the lecture notes where B and A are the like the wave function coefficients in region 1 and region 2. Okay. So next problem. R is infinite. Square velocity. This is the potential, and the width of the well decreases. And the width of the well decreases. What happens to the 0 point energy E naught in momentum uncertainty delta P? So this is our square well potential. Okay, and let's say its width is W. And so energy I think is easier to say, right? What is energy? N pi square h square over m, and here it's perfectly defined.
Yeah.
Yeah. So if W
Yes.
is decreasing, our energy will increase. Yeah.
Yes. Yes.
Yeah. For W double known, so our energy will be more this time. So it has increased. P greater than equal to P. What about delta P? So delta P. Okay. Do you want to answer this, Nana? It's very simple actually. Just use the uncertainty principle.
Delta P should increase because X is reducing.
Correct. So like h by w, right? Roughly, approximately. So basically inversely proportional. So our
Yeah.
delta p will also increase. So both will increase because we are confining our particle more and more. So we are reducing the uncertainty in its position. Therefore, the uncertainty in its momentum will increase. Okay. Okay. So I think we have done all 10 problems. So okay, we still have some time. Okay, we still have some time on our hands. So before going back to problem 1 and 2, why don't we discuss a few more problems?
Yes, sir.
Okay, let me okay, let me write the problem. Okay, for the nth state of our simple harmonic oscillator, evaluate delta x times delta p. Okay, so this is the problem, that we have a simple harmonic oscillator and we are currently in some nth state, we don't know, and we want to find out the product of uncertainty in position and uncertainty in momentum. So this problem is actually okay. So earlier also we did this thing, right, where we said that for a simple harmonic oscillator, our t and v both are same, correct? And because now it is in the nth state, so this will be okay, half of the total energy.
Which-
Yeah,
Yes, sir.
and then this will be 1 over 2m v squared, right? Momentum, and v is half k, and this will be squared. Yeah, and then this is simply, let me write this like this, n plus half. Okay, is this step clear? So I have
Yes.
written the expectation value of t in terms of p momentum, p square over 2m, and v potential energy in
Sure.
h square. Yeah. So our p squared here, our sorry, this p, actually this will be p squared. Yeah, like this. So our p squared is simply m h cut omega. 2 and 2 will cancel out, and n plus half. And our h squared will be h cut by m omega. Again, half will cancel out, n plus half. Okay. Now this is because we have our, this k is nothing but m omega square. Okay. So I have substituted m omega square for this k. That's why I am getting h cut over m omega. Yeah. Okay. So yeah, so we already discussed this delta x thing, right? So we know that this delta x squared is squared minus x squared, and this simply becomes p squared. Yeah, this we discussed that this expectation value of x is 0, right? Because this is a symmetric potential. So x becomes 0. And similarly, our delta p squared, this also becomes 0 as p squared. So so our delta x squared, delta p squared, then becomes, just multiply these two, this and this. So m omega cancels, it becomes h cut squared and n plus half squared. Now we can just simply take square root on both
Yeah.
sides, and we get delta x delta p. This is simply n plus half
This one.
h cut.
Yes, sir.
Now for ground state, for ground state, let's take one special case. Our n is 0, so our delta x delta p is h cut by 2, which is the minimum value, right? Which is the minimum value. So we can, basically what we can say is that our delta x delta p, this is always greater than equal to h cut by 2. When our n is higher, let's say n is 1, then this will be 3 h cut by 2. Yeah. So this, what basically, what with this problem what we were checking is that the solution that we find for our harmonic oscillator, does that violate the Heisenberg's uncertainty principle or not? So clearly it does not violate. It actually follows, and the minimum value is for the ground state, which is also the minimum value allowed by the Heisenberg's uncertainty principle. Now a good homework problem will be that you find out this delta x delta p product for some other case like particle in a box. Yeah. And there you see whether you are getting the same thing or not. Okay, any doubts in this one?
No, sir.
No.
No, sir. No.
Okay, then let's do one more, that we have a box, and it is in ground state. Okay, with A as 10 to the minus 10 meter, right? 1 angstroms. Calculate the force that the electron will exert and impact on the wall. Okay, so we have this particle in a box, right? And the width is 1 angstroms. And the electron is it's in its ground state, and it hits the wall, and we have to find out what is the force exerted during the impact on the wall. Yeah, okay. Generally, we do not calculate force in quantum mechanics, but it doesn't mean that we cannot, we just don't. So here, let's calculate for this problem what is the magnitude of the force when we consider some realistic values like 1 angstroms, right? So this is like microcoulombic specific that the electron is confined in. Okay, so the formula that we will be using to calculate force is this one.
ph08.
Okay, like it's
Why,
the
sir?
negative gradient of energy, right?
Why, sir?
So this is the okay. How okay, you know like integral is integral f dot dx. Is this okay?
Yeah.
Yeah. So I've just inverted here. So this is energy.
Yes, yes. Yeah, 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 yeah. Okay. Okay.
Makes sense now? Yeah. So basically energy is f dot dx. Yeah. Okay. Same thing. So because it is in the ground state, so our energy is E1. So n is 1 basically. So n squared is also 1. Pi squared squared for 2 a squared. Okay. And now we take the derivative. So d E1 by dt, and then we put a as 10 to the minus 10, and this will give us the force. So this is basically the answer, and then we will just solve this, put in the values, and get the force. So the derivative will be, so all this is just constant,
Hmm.
and this is because this is a squared, so we will get minus 2 by a cube. Okay, and we already have one minus sign here, so these two will cancel out. Okay, and we will get pi squared h cut squared over ma cube, and then we substitute a as 10 to the minus 10, and also value of pi, h and m. So when we do that, we will get f as pi squared, and this h cut is 1.054. This is 9.1 into 10 to the minus 31, and this becomes 10 to the minus 30. Okay, so if we calculate using the calculator quickly, so this is by we get 1.2. So this comes out to be 1.2, and 10 to the powers will be, this is minus 34, minus 68, minus 61, so minus 7 newtons. Okay. Now this tiny force, remember this tiny force is exerted by a tiny electron.
By calculating momentum also we can do it now. It is lengthy. By calculating momentum, particle in a box, we can also do it like that also, no?
The problem is uh, that the momentum operator is not an like the wave function here, that is not an eigenfunction of the momentum operator.
Yeah, yeah. Oh, okay, okay.
Yeah,
Yeah,
so you will not get basically p values like we get
yes.
e values here. Yeah,
Sure, 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 sure.
yeah, you will not get eigenvalues of the momentum. That is the problem. but
Yes.
but we do
Thank you.
have the energy eigenvalues, so we make use of them. Okay.
Sure.
Yeah. Okay. Okay, how about just one, okay, just one last problem, and then we'll call it a day, and then I'll also review problem 1 and 2, and that's it. Okay, so let's do one where we have uh, this potential barrier. Okay, so let's consider the same problem that we considered earlier. Let's say we have a barrier like this. Okay, just like we discussed in the earlier one. Let's say this is our region 1, region 2. Again we have this stream of particles like we had in the previous problem. Okay, and this is x is equals to 0, and this is v naught, the height of the barrier. Okay, now the question is, if E greater than V naught, show that sum of the fluxes of transmitted and reflected particles is equal to the flux of incident particles. Okay, so there will be some reflected and some transmitted. This was what we discussed earlier, right, when we solved that problem of the this barrier, and now we have to show that their sum of these two flux, that is equal to the flux of incident particles. So basically conservation of number of particles. Okay, so first of all we have to write the wave functions in region 1 and region 2. So the wave function in region 1, because our E is greater than V naught, right, everywhere, we will always have oscillatory solutions. Okay, so here we will have e to the iota k naught x. This is incident, and because there will be some reflected which will be moving in opposite directions, so we will have a times e to the minus iota k naught x. Okay, and then for psi 2, which is region 2, we will only have b times e to the iota kx. Okay, so this is x greater than 0 and this is x less than 0. Good. Notice that here we have just taken this amplitude to be 1. Okay, we have just considered that this amplitude is 1 because this term corresponds to our incident beam, this term corresponds to our reflected beam, and this term corresponds to our transmitted beam. Okay, so we have just taken this to be 1. Okay, and also note that here we do not have any wave which is traveling from right to left, right, because because there is nothing to reflect it back in region 2.
Yeah.
So now we have our uh, continuity equations, because our wave function has to be continuous. So when our x is 0, right, at x equal to 0, psi 1 equal to psi 2, right. So if we put x equal to 0 here, we get 1 plus a, and here we get b. So this implies 1 plus a is equals to b. Also our derivatives have to be equal. So psi 1 prime has to equal to psi 2 prime. If we take the derivative here, we get iota times k naught plus a times, and then this term becomes 1 because we put x equal to 0, and then this becomes minus iota times k naught and then a. So basically this becomes, if I take k naught common and iota common, so 1 minus a, right, because this terms just gives me iota k naught and this terms gives me minus iota k naught times a. So this, and this terms gives me iota times k and b. So our iota cancels out, let's cancel out iota. Yeah, so we have these two equations. Okay, so now what we can do is we can write a and b in terms of k and k naught. So using this equation 1 and 2, if we simplify, what we will get? We will get a as k naught minus k upon k naught plus k, and we will get b as 2 k naught upon k naught plus k. Okay, and we can check, if we do 1 plus a, we are getting b, and if we do 1 minus k multiply by k naught, we are getting k times b. So essentially what we have done, we have written a and b in terms of k and k naught. Okay, so flux of particles for the incident wave. Okay, so this is this. So flux for incident wave that is given by simply h cut k naught by m. So this is the flux and this is the incident one. And now we have to find the flux for the reflected wave and the transmitted wave. So for reflected wave, we'll have k naught, sorry, this h cut k naught by m, and then mod a squared. And then for transmitted wave, we will have k naught b squared. So these will be the corresponding flux. Notice here we don't have any coefficient because we took that coefficient to be 1. So if we add these two, basically what we will get? We will get h cut k naught by m. Sorry, no, this will not be k naught but k, because this is the transmitted wave, right? This is in the region 2. So here we have k and not k naught. Okay, so we'll have the sum will be h cut over m, and then k naught a squared plus k b squared. Okay, and then let's write this. So our a squared is k naught minus k squared upon k naught plus k squared, and we have a k naught here, we have a k here, and this is simply 4 k naught squared over k naught plus k squared, right? So now we can take out this k naught outside. So h cut k naught over m k naught plus k square, all this comes outside, and inside we are left with this plus 4 k naught. Okay,
Yes.
so if we open this, what we will get? We will get k naught squared plus k squared minus 2 k naught, and because this is plus 4 k naught, so ultimately that will become plus 2 k naught. Okay, so h cut k naught over m k naught plus k squared, so k naught squared minus, sorry, plus k squared and plus 2 k naught. Okay, and this is simply k naught plus k whole squared, right? So I can cancel out these two terms, this one and this one, correct? Both are simply k naught plus k whole squared. So what we are getting, that we are getting the sum as h cut k naught over m, which is same as that of the flux for the incident wave, h cut k naught by m.
One question: how did you write the incident flux at h bar k naught by m?
Oh, this one?
Yeah, h bar k naught by m. How did you get this as the incident flux?
Oh, okay, so I can tell you two things. First of all, here the coefficient was 1, so I have not put the coefficient. Okay, that's
Mm-hmm.
one thing. But
Yeah,
if you are asking how do I get this form of this hk over
yeah,
m,
yeah.
Okay, so if you want, I can I can tell you how it comes. I mean, there is a small kind of derivation kind of a thing.
Yeah.
Okay, so okay, so we have, the probability current density. We discussed that in the
Mm,
previous
yes,
class.
yes. Right, right, huh.
Yeah. Okay. So basically, flux is nothing but current, right? Correct? Because your particles are flowing over time. Yeah. So current and flux are interchangeable words.
Okay.
Okay. So we have, let's say, okay, let's consider, let's say our psi is like this. Okay. The wave function, like the oscillatory wave function,
Mm-hmm.
it
Yeah.
has some coefficient a. So then, what is the current? This one, right?
Yeah.
This is the current,
Yes.
and this is also
Yes, sir.
the flux, right? So
Mm-hmm.
you can also call it flux.
Okay.
Yeah. This is the amount of particles that
Flow,
are
huh.
flowing. Actually,
Flowing. Okay.
this is the probability current, not flowing. So same
Yeah.
thing as
Right.
flux.
Okay.
Okay. So let's solve this thing. Now here, because a is constant, so mod of a square will come outside from every term, psi, del psi, whatever. Yeah.
Yes.
And then because this is psi, so we'll have iota kx, then minus iota k here, and then minus iota kx. So this is our
Mm-hmm.
first term, and then
Mm-hmm.
minus e to the minus iota kx, and then iota k this time, and then e to the plus iota kx. Correct?
Right.
So basically, these terms become 1.
Mm-hmm.
Yeah. And this is minus iota k, and again minus iota k.
Mm-hmm.
So minus 2 iota k. So
Mm-hmm.
just remove all this thing and write minus 2 iota k into minus 2 iota k.
Okay.
Correct? So these two cancel out. Iota square becomes minus 1, and this minus is here, so all this also cancel out. Basically, what we are left with is this h cut k over n mod a square.
Modulus of x. Yes, sir. Good. Thank you, sir.
Yes.
Is it clear now?
Yes, yes, yes. Thank you.
Okay, so yeah, that's it for today. So sir, you can leave if you want. I'll just quickly explain problems 1 and 2 to ma'am,
Thank you, sir.
Yes, huh.
Thank you, sir.
we
So I
will
am
end.
leaving.
Okay, thank you for joining.
Okay. Thank you, sir. Thank you so much, sir.
Yeah.
Very nice interaction.
Okay, so let's go back to problem 1 and 2. Yeah, here, yes, this is problem 1.
Okay.
So this was particle in a box, right? We
Uh-huh.
have 0, potential is 0, between 0 and a, and infinite otherwise. So we have this particle in a box. Okay,
Mm-hmm.
so we are given a wave function. This is the wave function that we are given, and then we have to just normalize it. So the one thing is that the given wave function is written as a product, and the options are given as a sum. So first thing
Mm-hmm.
that we did was we converted this to using this trigonometric identity,
Right,
converted
right,
this
right.
to a sum.
Mm.
Yeah. And then once we have this psi, we then we then just simply integrate mod psi over the entire
Mm.
space, put that
Mm-hmm.
equal to 1, find out what a is, substitute a back, and then we get the answer.
Okay,
Yeah. So just the question was just if you know this trigonometric identity or not.
okay, okay.
Yeah.
Take, right.
Then yeah, second problem was that we have a harmonic oscillator in its ground state and we are given the wave function, that this is the wave function.
Mm-hmm.
And then the question says that the probability density is maximum at x is equals to 0 and we have to tell whether this is true or false.
Mm-hmm.
So because we are given the wave function, we square it here and we find out the probability density. And because we have to find out its maxima, we take its derivative,
Derivative. Okay.
equate that derivative to 0,
Mm-hmm.
and we see that okay, this is the derivative that we get, and we see that x is equal to 0 is a solution. So
Okay.
uh, like either a minima or a maxima, and then to confirm that it is a maxima we have taken a double derivative and
Mm-hmm.
we find out that this double derivative is less than 0, which means it is a maximum. So the statement is true.
Okay.
So it is just taking derivative of this function two times and
Okay.
putting x is equals to 0. That's it.
Mm-hmm. Mm-hmm.
So these were the first two problems.
Thank you so much. Thank you so much.
No problem.
Yeah.
Anything else that you want to ask before we end
Yeah,
the session?
actually, I wanted to know that if some wave function is given
Yeah.
at the initial wave function,
At t is equals to 0.
sometimes for for a free particle, sometimes particle in a box, or sometimes in any situation,
Okay.
maybe in
Any
simple.
general wave function.
Yeah,
Yeah.
and then we are asked to find the wave function at any time t,
T.
the
Yeah.
time dependent wave function
Correct.
later on. So, what is the procedure? But
Okay. So the procedure is very simple. If you remember in the last session, we solved one such problem.
mhm,
So the thing is that there is this factor e to the minus, e to the iota et by h cut. Yeah.
e to the power, sorry, e to the power.
Iota times e times t by h cut. Yeah.
Yeah, yeah, that is a time dependent form.
That
Yeah.
is the time dependent form. If
Yes,
we
yes.
multiply this factor, then what we get is we get the time dependent wave function. We have to just multiply this with the wave function at time is equal to 0. Now the only thing that we don't know in this factor is the energy E.
Mm-hmm.
Yeah. So depending on the problem that you have, let's say for example we have a particle in a box and
Mm-hmm.
you know the energy of the particle,
Mm-hmm.
then we can just substitute that energy
Mm.
and we'll get a time dependent wave function. So the procedure is find the wave function at t is equals to 0. Okay.
Uh-huh.
Then find the energy of the particle using the time independent Schrodinger's equation. Yeah.
Mm-hmm. Mm-hmm.
And then put that value of energy into that factor, the exponential factor, and that's it. That now gives you your time dependent wave function.
No, sometimes the wave function which is given, it is not the same wave function. Like for a particle in a box, it is under root 2 by L sine of n
Yeah.
pi x by L, right?
Yeah.
But sometimes in one of the problems in one of the assignments, it was given that psi x for a particle trapped in a potential well, it is a times bracket L minus x, something like that.
Okay.
So, which is not in the form of sine of n pi x by L.
Correct.
And in that case, what to do? Like that was in simple harmonic motion. If similar thing is given for simple harmonic motion or any other situation, then how
Yeah.
to proceed when
So
it doesn't look like?
for
Uh,
example, when they explicitly mention in a problem that this is a simple harmonic oscillator, yeah,
mhm.
then you have to just consider that it's in the ground state. Okay, if they have, or not necessarily, then basically you write your energy as n plus half h cut omega.
Mm-hmm.
Okay, now you have this energy. Just put this energy in the exponential form. Okay, and
Okay.
multiply with whatever wave function that they have given.
Okay.
Yeah,
Okay.
because that is your wave function at t is equals to 0. Now this factor decides how your wave function evolves with time. Whatever wave
Mm-hmm.
function we have at t equal to 0, that remains as it is. Nothing
Okay.
changes in that, and
Huh.
we just multiply this factor to basically give us the time evolution part,
Mm-hmm.
right?
Sometimes, we calculate the coefficient Cn using momentum momentum space wave function. Is it, am I saying something correct or
Uh,
wrong? Some Fourier transform or something like
yeah.
that.
Okay. So, like for example, today we did this one problem where, yeah, this one, no, the E naught P naught one, right? I didn't, this one, this P naught E naught. So,
This like C1, C2, है ना?
yeah. So, like there are two things. Okay,
Hmm.
understand. Like for example, in this question, we are given the values of C1, C2, etc., right? And
Mm-hmm. Huh.
using these values, we are calculating the expectation energy. Now,
Okay.
now what can happen is, let's say they give you the value of the expectation energy,
Huh.
and then they ask you to find out C1, C2, etc.
Okay.
Okay,
Huh.
but they have to give something, because why? Because these C1, C2, they have some constraints. Like one constraint is that this sum of their mod square has to be 1, because that is the total probability, right? So for example, here if you see, this 1 by 3 and 2 by 3 will give you 1. So this is one
One.
constraint.
Mm-hmm. Okay.
And another constraint is like some physical quantity, like for example here energy. So if they had told earlier that the expectation value of energy is, let's say, 11 by 6 h cut omega, and your wave function is a combination of your ground state and second excited state wave function.
Mm-hmm.
Okay, let's say that this was the problem. Then you have two conditions for these two unknowns.
Okay.
One is that their sum, like their total probability has to be 1, so their mod square sum is 1. And
Mm-hmm.
another condition we are getting from energy, right?
Okay.
That if we do this expectation value of energy, then our total energy should come as 11 by 6 h cut omega. Yeah, 11 by 6 h cut omega. So
Okay.
then we have two unknowns and two equations. So that will give us C1, C2.
Okay.
Now
Okay.
in general, if you have, let's say, C1, C2, C3, Cn,
Mm-hmm.
then you will need n such conditions to precisely determine what values of C1 and C2 you have. Okay.
Can you suggest some book? I would like to do solve more of similar problems. I think that will help me in understanding this concept.
Uh, I would suggest Quantum Mechanics by Griffiths.
Griffith, which chapter? I have Griffith. I have Zetley.
Exactly, Griffith, they have very good solved problems at the end of all chapters. So, for example, there you'll have chapters dedicated for simple potentials like 1D box, 2D box,
Okay.
this
Okay.
harmonic oscillators.
Okay. Okay.
Okay, so
Okay.
you'll get
Let
those.
me search. Okay. Let me search in the books.
Another good resource for such problems, because you
Mm-hmm.
saw that most of them are MCQ type or true false or numerical answer type. So another good source will be to look for previous year papers of like NET, for example, or GATE, for example, maybe IIT JAM if you want one
Okay.
level below.
Okay.
Yeah,
Okay.
so you can easily find previous year problems.
Gate and jam.
GATE,
Gate and jam.
JAM,
Physics.
even NET also will have some good
Okay.
questions.
Okay. Okay. Net. Okay. Okay. Got it. Got it. Got it. Yeah.
There is one
ठीक.
website called Physics by Physics. They
Okay.
have
Okay.
they have their problem sets
Mm-hmm.
separated by individual chapter.
Mm.
So for example,
Mm.
you will find question bank for quantum mechanics separately.
Okay.
Yeah,
Okay. ठीक
yeah,
है,
you
got
can
it.
do that.
Yeah.
Okay,
Thank you so much. Yeah.
nice.
Thank you. Yeah. Thanks.
Okay, okay,
Thank
then
you.
we'll end today's session. Yeah,
Thank you so
have a
much.
nice
Yeah.
day. Bye
Yeah.
bye.
Thank you. Bye.